change it. The output dependence is O, and here is output dependence. Here also need to change S2 read, S2 write at the same location. Okay, S1 and S2 write to the same location. So we need to change that. Okay, there is input dependence, but it is not of any concern because output dependence, input dependence has no problem. Okay, so we remove that. Okay, because read at the same location does not cause any problem. Okay, only this tree has problem. So that's the reason why the tree is here, except for input dependence. Okay, in order to solve this false dependency, which is anti-dependence and false dependence. Okay, false dependence means it is not real dependency. It's actually a false one. True dependency, you cannot do anything. False dependency, you can do something. Okay, for both of them, the solution is to use renaming. Okay, variable renaming. So you just need to change the name of the variable. For example, in this case here, these two, they look like they have right after read. Okay, right after you read. Okay, this is false dependency. You just need to rename it because, of course, this sum actually comes from here, and of course, this one is dependency between two of them. Okay, but we're talking about this and this statement. Okay, so this actually comes from here, but actually it's not important in this case. You actually override the sum, but you can use a different name, right? So suppose you put sum 1. Okay, here's sum, and this one sum 1, so there are two different variables. Okay, if you change here, you have to remember to change here. Okay, because this sum is relying on this, so here should be sum 1. So here's sum 1, and sum 1. Okay, that will solve the right after dependency. If you do that, now this 2 has no dependency. Okay? If you don't change, then these 2 is dependent on one another. You cannot run them in parallel. Okay? If you change or you rename them, now they can run in parallel. Okay? So that is anti-dependence, which is false dependence. The output dependence, also same thing, is also false dependence, and you can avoid this output dependence by changing the variable name. So the solution for both of them are the same. Okay? So what are these output dependence? You can see these two they are writing into you write here, and also you write here. Right? So you write after you write. So this two actually has false dependency. You cannot run them in parallel, okay? In the original form. But then if you change the name here, let's say this one sum 1, this one sum 2, for example, in this case, you have to change the name, right? So right now they are not dependent on one another anymore. Okay, so to solve dependency, you can rename them as well. Of course, if you change here, you have to change here as well. Because this actually use this, right? So here's sum 1, here also sum 1 as well. Okay, this sum 2, actually this problem and the previous problem is the same problem, just that they're looking at two different statements. Okay, these two, false dependency is right after read. Okay, these two is also false dependency, is right after right. Okay, so we're talking about these two and these two. So in this same example, we have two different kind of false dependency, and both of them can be solved by renaming. Okay, contrary dependency is related to anything that is related to a condition like this. Okay, why is it called control dependency? The flow of the program depends on the data. Okay? That means we change the flow of your program execution. For example, in this case here, if D is equal to 0, then it will continue. That means it will not get past this point. It will not execute S2. But if D is not equal to 0, then it will not continue, and therefore it will do this statement here. Okay, so this statement is executed or not executed, depending on the condition that whether it's true or false, condition that is seen. Okay, so there is control dependency. Okay, the dependency depends on whether the code is the condition is true or is false. Okay. Now, dependency, most of the time, when we look at cloud computing, why do we need to look into it? Because if you don't do anything to it, you cannot do any cloud computing. Okay, so you have to adjust your code, and you have to recognize the dependency within your code. Okay, and you make the necessary adjustment. For example, just now what we learned before, if we don't change the code, we leave it as it is. It actually depends on one another. It's false dependence, and you cannot run them. Okay, but if you adjust it, if you know that it's false dependency, that means you can modify it by renaming. Then you can solve the problem. Okay. So here, dependency in the loop. So we want to look at what kind of dependency in the loop that we can improve in order to make our code able to be parallelized. Okay. We have two different types of dependencies. One is loop carrier dependency. The other one is loop independent dependency. So what is loop carrier dependency? Okay, loop carrier dependency looks like what I showed you there. In the loop carrier dependence, the statement in the iteration of the loop depends on the statement in another iteration of the loop. So here we got a for loop. How many iterations that you have to run here? 4, right? You have to loop 4 times. Okay? It says here, loop carry dependency, that means your dependency is actually carried forward or carried backward. Okay? They are both carried. Loop carry. Okay? How do I identify it? Look here. In this iteration, you see, maybe I just won't go ahead. In this iteration, the vector B, or I should say array B, let's say iteration 0, maybe iteration 1, let's say iteration 1. Okay, in iteration 1, this statement is using B1, okay, and it will put it into B1. But then in this second statement, I also access A1. Okay? But then here, actually depends on the previous element of B. Okay? The previous element of B, which is done in the previous step. So that is loop carry dependency. Okay, in iteration 0, 1, 2, 3. Okay, so statement 1 will cause B0 to be 8. Right? There's statement 1. Statement 2 will cause A0 to become, but this one has a problem actually, because we do not have minus 1. Okay, I think we need to assume that there is some value before. Okay? Assume that the value before, I'm not sure what it is. Okay, that means it has iteration minus 1. Okay, B minus 1 has it, but it's assumed that we have a value here. Okay, so that is not question mark, it's actually a value that comes from here. Okay? So this is iteration minus 1, right? And plus 10. Okay, so in iteration 1, S1 actually is B1, you assign it into it, and then S2, you calculate A1, and this value here, which is B minus 1, actually comes from E. Okay, so this is loop carrier. You carry this dependency from the previous one to the next iteration. That means it depends on the previous one. It can depend on the future one. It also can depend on in the past, the value that is updated in the past. Okay, so this one is loop carrier. If let's say this one depends on the B from here, then that is not loop carrier. If let's say this one is B1, then it's not loop carrier. If B0, then it's loop carrier because it's the previous iteration's result, not the current result like the previous one. The same thing here. Your B is B2, you assign A, S2 is A2, and then B minus 1, 2 minus 1 is 1, right? So this value here plus 10, this value here actually relies on the value that you compute in the previous iteration. So that is the meaning of loop carrier dependency. Okay? So this kind of dependency is a problem. Why? Because if you don't you haven't execute this yet, right? That means this one actually depends on this. You have to execute this one first, then only you can execute this. You cannot run them independently. Okay? Remember when we do OMP, we do OMP parallel 4. Remember the 4? Yeah. So what actually it does in the background is that you look at how many iterations that you have inside there. So when you use OMP parallel 4, it looks at the for loop, the next line for loop, it looks at how many iterations that you have there. So if let's say you got iteration 0, 1, 2, 3, okay, there are 4 together, right? So you will assign this iteration 0 to be executed by track number 0. And this one is executed by track number 1, this one track number 2, this one track number 3. Okay? Right? Now we have a problem. Why? Because this track 1 depends the value of this. And this one is supposed to compute by track 0. Isn't that dependency? Yeah? So if track 1 depends on track 0, there will be dependency. That is the carrier dependency. And you cannot solve this problem. Okay? Let me not say it can solve. You cannot run that in parallel. Why? Because this T is 1. In order to execute it, you have to wait for T0 to finish first. How about T2? T2 cannot finish if T1 doesn't finish. If T1 doesn't finish, it cannot finish because T0 hasn't finished. So it depends on it, so it depends on that. Same thing here. T3, it depends on the previous result, because it depends on this here as well. And this one also depends on this. This one is dependent on this. So they are dependent on one another. And this loop carrier causes OMP4 to fail, to execute in parallel. Okay? Now if I change the code slightly, of course it will not be the same result if I change it here. Suppose this one is not B minus 1, but it's B0 as well. That means here, it's not I minus 1, but it is I. Okay? And suppose here also B1, because I don't change the code already, so this one is B2. Now this one is not dependent, this is not dependent on the previous one. This also not dependent on the previous, but it depends on this. This one depends on this. Now it's alright, right? If we use OMP parallel 4, and OMP parallel 4 will assign this to track 0, track 1, track 2, track 3. But each one of them are independent of one another, because you see inside here, it doesn't depends on the result from other iterations. So in this case, this can be executed, all of them can be executed in parallel. Do you agree? Because they don't rely on one another. The result, of course, these two is dependent on one another, but it's executed by the same time. That means before you execute this, you have to execute as one. So these two is dependent, but it's fine. Within the iteration itself, if they are dependent on one another, it's fine. But it cannot depend on the result from the previous one, either from before or from after. If it depends on any one of them, that means you got carrier dependency and you cannot do in parallel computing. But in this case, yes, you can do it in parallel computing because they depend on the statement within itself, that's fine. And these can be executed independently from one another. Now you can run them in parallel. Okay? Now, of course, this example is different from that. Therefore, this actually not answers that question. We are not solve that problem. Okay? But there's a way to solve it. I'll show it to you later. Okay. This is the one that I mentioned to you. Just now is loop carry dependency, right? Okay, loop independent dependency. In loop independent dependency, loops have inter-iteration dependency, but do not have dependency between iterations. Okay, it has dependency among itself, but it does not have dependency before and after. Okay, so that is loop independent dependency. Okay, each iteration may be treated as a block and performed in parallel without other synchronization. This basically explains what I talked about just now. Okay, so this one is loop carry dependency. Okay, and then this one is loop independent dependency. So this one I can run them in parallel. Okay, simple rule of thumb, because we saw that problem. A loop that matches the following criteria has no dependency and can be parallelized. All assigned to the shared data are into the array. Okay, you see that we use array here, right? And each element is assigned by at most one iteration. Okay, so that means when we do the assignment, we only done it within the iteration, not in other iteration. If it happens in other iteration, then you have to carry it. Okay? And then no iteration reads element assigned by other iteration. For example, in this case here, if we rely on the previous one being read from other iteration, then you actually satisfy this. That's why you cannot run them in parallel. But if you can contain them, you change within the iteration, and also you use within this iteration, then it's fine. You can actually allow this iteration to be executed independently. Okay? Okay, so let's have a look at this example here. 1, 2, 3, 4. Can you find out whether there's any? Can we do? Or I should ask: is there any loop dependency? Loop carry dependency. Let's take the first example. Is there any loop dependency there? It looks like there is a dependency, but actually it's not. Why? Because we are just reading. There is no iteration that is writing. Okay? Can we run them in parallel? You see here that it looks like it has a dependency because it's reading from the previous I. Right? Right now? But then here there is no loop carry dependency because this I is not, oh sorry. So it actually writes to itself. So is there any carry dependency for this? Sorry, I mean, just now what I mentioned is not right because I forget that actually it writes to itself. Okay, so is there any loop carry dependency here? There is, right? Because why? It actually write to itself. And therefore, the next iteration which rely on this A minus 1 is going to have problems. Okay, so that is loop carry dependency. How about this one? The second one. Is there any loop carry dependency? It also has, right? Because it's actually relying on the other part as well. But this one, actually, there is a special property. Because if you look carefully, it's actually by batch. this. When you read, you are reading from n divided by 2. So it's one batch and one batch like this. Okay? It relies, but it doesn't rely on the previous iteration, it relies on the previous batch. Okay, this one you can solve. Okay, this one you can solve because it might be like this. Right now, currently you're running this in parallel. Okay, but once you finish, you move on to this. Yeah? You move to this batch. And this one actually relies on the previous batch. The previous batch. It doesn't rely on the previous iteration, but the previous batch. Because it's already computed before you move on to here. You already have the solution here. Okay, here you run in parallel, here you run in parallel, but these two do not run in parallel. Now these ones do not have loop carrier dependencies. Okay, so you have to look at the situation and also what kind of problem that you are, how the problem is solved can manifest itself, whether there's any loop dependency or no loop dependency. Okay, so how do we parallelize this code? Okay, how do we parallelize this code? How do we remove the dependency? This slide here does not talk about it. Actually here, this slide actually talk about it. So how do you remove dependency? Okay, you can see here, this one has dependency because it is writing to A, and also it depends on the future A plus I. Okay, that means if you run them in parallel, okay, this last statement here, this statement is dependent on the future, or it will depend on the next iteration, which is executed by another thread. Okay? So it's going to depend on T2. T0 is going to depend on T1. Okay? So you cannot run them in parallel. So what kind of dependency that you have here? Of course, it's very obvious. It's loop carrier dependency. Alright, here it shows to you safe loop makes parallel. Okay, so this is the is this the same example just now? It's different, right? Yeah, it's different example. Okay. Okay, let's look at this. I'm not sure why we use a different example there. Okay, at the top here, you see that you have dependencies, right? See that? There's a dependency there. And then at the bottom here, oh sorry, actually this one is to solve the previous one. So we've got two solutions, you can see that. Okay, so this A is the array that we are looking at. But you see A2 there, A2 is another array. Okay? So you can solve it by using two different arrays. Okay? So if you solve using two different arrays, then they don't depend on one another. So this allows you to solve the previous problem. So it's good by using two different arrays. Now another way to solve it is by using this technique. Okay? So what you do is you first you assign that, or you create another array which is A2. Maybe I should drop that. This A2. Yeah, I can highlight. So this A2 there. Okay, we are trying to solve this, right? And this is the solution. So first what we do is we copy this A into A2. Okay, we copy it into A2. So we got two arrays. Okay, and they are the same. And then here, instead of relying on that A itself, we rely on A2. Right? So right now, you don't have a dependency because if you look at the previous code here, it relies on the next one, right? Rely on the next one plus this value. Okay? So what you need to do is you need to create another variable here. You add it first. Okay, you add it first. So you have another array with a solution array. And then when you solve this solution here with another loop, although it depends on the data, but this array is another array that has been updated. I think there's something not quite right here. This one should be here. Okay? This plus x should be here, and this one without plus x. Okay? Because if you do that, now you can see that A2 is an independent array. Okay, so it does not depend on the previous value because it's already done in the top portion. Okay, so you actually split them into two different parallel computing code. So this one can run in parallel. This also runs in parallel, but two different pieces. And you create additional vector in order to hold the value. I think there's a mistake there. This plus x here should not be there, it should be okay, so if you do that, these two can be run in parallel. Okay, the top one can run in parallel, the second one also run in parallel. But this two is not parallel. It runs in sequential. So you can run this, let's say 16 threads here. If let's say n is more than 16, let's say 16 threads here. And then here, another 16 threads. Okay? The two actually run in serial, but within the for loop, they can run in parallel. Okay? So if you do that now, there's no dependency here because the result of A2 has already been computed before that. You finish first, then only you run the second one. So that is one way to solve. Okay, let's look at another example here. Okay, this example shows the dependency. Okay, in this breakbox actually is the iteration number. So this is the iteration before, the current iteration, the next iteration. Okay, so that will be our I. Now, if you look at the C, which is the second statement, okay, you're using this I. Okay, how about A? You're also using the I, so no problem. So you're copying this content, this value here, into this A, so no problem. Okay, so the second statement actually happens within the iteration, so no problem. But how about the first statement? This statement. That statement actually relies on the result of A, which is of the previous iteration, this iteration. Okay, the content here, you copy over here. That's the way you see that. Okay, so now you got a loop character dependency. Okay? So just now we saw by creating another array, okay, and then that array we use it later on in parallel. So that's one way to solve. Another way to solve is to shift. Okay, so this is actually in this form, right? So this one's on loop dependency, loop character dependency. But if we shift this array slightly to the left, one step to the left, okay, and you just focus on this, now you find out that you can run that in parallel. Okay? Why? Because you already shifted, so this is in this iteration, the B1 is, sorry, the B array that we are looking at this iteration is actually I plus 1. Okay? Now you can take this value, and then you assign it to this A of this, you assign it here. Okay? So if you do that, then your code is going to be different, but you solve the problem. You can run this iteration in parallel. That means you can assign this thread to each of these iteration and execute. Okay, let's have a look at the code. What kind of changes that we need to make? Okay, two things that we need to make. The first one is to move out the first part of the second statement, which is B1. Okay, we have to move it up here. Okay, so in iteration 0, you can see that I is 0, right? I is 0, and this one is 0 plus 1 is 1. So that one is done independently, outside this parallel form. We have parallel form. Okay, with a sign first. Okay, now within here, okay, although it relies on the previous one, but no problem because you already have the breakdown there. Okay, so in here, when you execute, it does not depend on the previous iteration. Okay, so when you assign, let's see, whether it's the same code or not. I think it's the same, right? Yeah, it's the same. Just that it changed the position, is it? Right, change the position. Okay, this one is actually the second statement. This one is the first statement, but here it changed. There's no difference there. Okay, just imagine that this is the first, this is the second statement. So it's still the same. So in this case, even though it is relying on the other iteration, but this one solves the problem because we already computed in the first part. Okay. Now another change is if you do that shifting. Now your program has changed. You have to update your A differently. Sorry, the last A you have to update because it's going to shift. Okay, so in this case, the last iteration after here, we just execute one more time, which is to handle the last an plus, which is basically this, because you have to adjust this by subtracting n minus 1. Okay? And take also, what you do here is your I is start from 1 and not 0. Start from 1. This is previously was n, and right now you have to subtract by 1, n minus 1. Okay? And iteration 0, you have to do it there. The last iteration, which is this one, you have to do it once. Okay? So basically, what it does is this. It's still the same. Initially, this was inside here, and therefore this one is 0. This one is inside here, therefore this one is okay, but right now we break them up. So we start from 1. This is iteration 0, iteration 1 until n minus 1. Okay, and this is the last iteration n. Okay, so basically by doing that, we can actually break the loop character dependency. Okay, basically what you're doing is this. Okay, so it's a little bit of hard work, but right now. This parallel computing here can be executed by multiple threads, and you don't have to worry about they relying on other components that is computed by other threads. Okay, so you break the dependency. Okay, that's how you identify where the problem is and how you solve it. Okay, if you don't solve that, then it means you cannot run them using this web parallel form. You fail to run the program. Okay, so that I finished that. Okay, next we want to move on to something similar like what we have seen before, the condition. And this condition is it was first described by Bernstein, A.J. Bernstein. And we have seen this condition before. Okay, now we repeat here, but right now we are talking about the iteration. The instruction or the statement. Before we were talking about the dependency between iteration, but right now we are going to talk about the parallelism within the iteration itself. Okay, so the input set or read set. We call it RI. Okay, consists of memory location examined by the statement of instruction A1. Okay, And the output set is WI, or write set, consists of locations where it is written. Okay, it says written, actually it can be written into by instruction key 1. Okay, this is just a terminology. Okay, let's look at the condition. Okay. Now we have two different kinds of set. The first set, just now you see, is the read set and the write set. Right? Okay, so you have to look at the instruction, whether the instruction involve any read set or write set. Okay? Sorry. If the iteration has read set and write set. Okay? And in order to ensure that it can be run in parallel, these are the conditions. The read set of is the first statement, and the write set of the second statement. Okay? They cannot overlap. Okay? If it overlap, it must be none. Okay? If it is non-overlapping, it must be here. Okay? If you have this kind of result, that means it passed the first condition. That means you can run in parallel. But not yet, you have to look at the other two still. Okay? Now the second one is to look at the second write set. Okay? Whether it overlaps with the read set of the second statement, and look at it and compare with the write set of the statement number 1. If there's no overlap, that means it is also free from dependency, and therefore it satisfies the second condition. And the third condition is write and write. Okay? You want to check whether the first statement, the write set, coincides with any statement in the write set of the second statement. If there is no overlap, that means it's null, and it's satisfied, yes, and therefore they are good for parallel computing. Okay? So this condition is something similar like what we have seen before, what we are talking. Yeah, I did mention it. So, first condition is you does I1 of the instruction 1 or statement 1 does not write into the location that is read by statement 2 or instruction 2. Okay? And then the second rule is that I2 does not write into location read by I1. I means instruction. Okay? And then iteration I1 does not write into the location that is written by iteration 2. So it's write to write. This is write to location that is read. This write to the location that is read in the reverse way. Okay, so basically it is this same condition that is seen down below. Okay, except that it's written in this form. Okay, so we want to identify using Bernstein condition to find out whether it is eligible for parallel computing. So this actually describes what we talked about just previously. Okay, except that we write it set. Okay, so let's look at this example here. So this is instruction 1. Just now we always use statement 1. I'm not sure why right now we change to instruction 1. Okay, just imagine that there's statement 1, statement 2, statement 3. Okay, and I and S is the same. Okay, in statement 1 or iteration 1, you can see that I read from A to B, right? So you see read set 1, A to B. Okay? And I write into X. So I write into X. So write set for statement 1 or iteration instruction 1 will be X. Okay, so read set R1 is AB, write set R1, W1 is X. How about the second one, the second statement, the second instruction? What do you read from? You read from BCD. Read from BCD. So read set for this instruction 2, statement number 2, is BCD. How about write set? Write set for instruction number 2 is Y. Because it's right into Y, right? Okay, how about Z? Z is also the same thing. For the read set is actually this one is 2 times X. So actually it's x, we don't take 2, but 2 is a constant. X is the variable, x is the one that we put in. There's a mistake that there should be a star, x star 2, that means x times 2. Okay, so it's x, and then a and e, so a, e there. Okay, and then when you look at the right hand side, left hand side is a right x, so the side right to z. That's why the right side is there. Okay, so now we are ready to actually find out whether this is possible to execute them in parallel. Okay, so when we look at the condition, we have to compare all. We cannot compare just one. Okay, so we want to find out this. Is it possible to run these two in parallel? That means I1, I2. Okay, can we run these two in parallel? Okay, so that's a question that we ask. Can we run these two instructions in parallel? That means this run by track number 0, this one run by track number 1. Is it possible? In order to find out that, we have to use this condition, the first time condition. Okay, this first time condition. The first one is that R1, W1, sorry, W2. The second condition, R2, W1, R2, W1, and then this one is W2, W1, W2. Okay? Okay, so let's see this. For I1 and I2, so we have this and this. Is it coincide with one another? No, it doesn't coincide, so it's not. Okay? Because there's no y there, there's no a and b there, right? So it's going to be no. How about this? R2, and this set W1. There's no x there, there's no b, c, d there, so here it's also 0. Okay? How about the last one? The last one is this. This 2 here. It's also not coincide, so it's 0. No, that's not 0. No. So that means this one can be run in parallel. It's possible. Okay? Okay, so let's look at the second one. Can we run these 2 in parallel? Okay, so we put I2, I3. Okay, the question is, can we do this in parallel? The same thing, we have to do this to find out the condition, W3, R3, W2, W2, W2. Okay? Okay, here I have to change because I have to follow this number there. Okay? And here I was following this number. Now I'm following this number, that's why I have to do this. Okay, so let's have a look. R2 and R3, the W3. There's no Z there, there's no BCD there, so it's 0. Okay? How about the second one? R3 and W2. There's no Y there, there's no X, there's no A, there's no E there, so it's 0. Not 0, sorry, it's not. How about these two here? There's no Y, there's no Z there. That means it doesn't coincide here as well. So these two also can be run in parallel as well. Okay? Right, so let's have a look at the last one. The last one will be comparing this and this. And we have to do that as well because when we run in parallel, this can be run by T0, T1, T2. Okay? Although this one, you look at it, it has some other instruction in between. It doesn't matter because we want to find out whether all this can be run in parallel. That means this one run independently by one thread, this one is on a thread, and this one is on a thread. So we need to compare these two also. Okay? So that is I1 and I3. Okay, so the same thing, we have to draw like this, R1, W3, R3, W1, and W1, W3. Okay? So 1 and 3. Is there any Z there? No. Is A, B? No. So it's 0. Oh, sorry, it's not 0, it's now. Okay, and then the second is R3, R1, R3 and W1. Okay, so you see here, there is an X. There is an X. Okay, there is here, there is no A, there is no E, but this coincides, so there is sunset there, which is not now X. Okay, so like that. So it's not 0, it's not now. How about the last one? The last one is right into 1 and right into 3. 1 and 3. X and Z. So it does not coincide, so it's 0. Oh, sorry, it's not. Okay, so in this case here, we see that this is now, but this is not now. And therefore, this one cannot run in parallel. Okay? So it means only these two can be run in parallel. Okay? But then these two also can be executed in parallel. Okay? But these two cannot run in parallel. That means I cannot assign a list T0, T1, T2. No, it's not possible. But I can assign a list T0. Okay? This one can be executed by T0. And then these two executed by T1. Okay? Oh, sorry. These two can be executed by different thread, but these two cannot, right? So what I do is I take this and this run by the same thread, and this one is different thread. So let's assign it. So I can do this T0 and T0. This one T1. I can do it because these two is dependent on one another, right? It's proven here. Okay? And how do I execute? This one must come after. So execute this one first, then only execute this in one thread. And this one can be executed in another thread. So you can split that into two threads. This is one. This two is one thread. You cannot separate it. Okay, and this one must come first, and this one must come later. Is that clear? Okay, so by looking at this Bernstein condition, you can conclude this way. So if you see that is now, that means they are independent of one another, so you can run that independently. But if you see that it cannot run independently, that means these two must be executed in sequence, the same sequence. Right? If this one comes first, this one comes later, this one must be executed first, and then this one executed later. And then this one must be, these two must be run by the same thread. Yeah? Okay. You cannot do like this, right? You know that this one is run in the same thread, and then you run this one first, then you run this. No, you cannot. You have to run this one first before you run this. Okay? So you have to go in that order. So somehow you can see that from this study, you can see which one is able to be run independently, which one you can't. Okay? Okay, so this end this slide. Let's move on. Okay, the next one is the algorithm. What kind of algorithm that we have? The content of this topic is still introduction. Actually, we have into introduction many times already. And we want to look at the model. We want to analyze the sequential algorithm. And we want to analyze parallel algorithm. And we want to look at what is the limit. Amdahl's law is actually talking about the limit. He actually explained something that is, it looks very weird, but then the law actually put a limit on how much parallelism that you can do. Okay? So once we come here, we will see. Okay, the question in here, roughly, it means it states this. If let's say I have parallel computing power, okay? Currently our GPU can have 2,000 cores, okay? And you say, okay, 2,000 cores we can improve, right? So I always tell you that you can prove the maximum is 2,000 times faster, but we don't get there. we don't always get that. There's certain limit, okay? Maybe you can get 100 times faster, maybe 1,000 times faster, but even though we increase the number of cores, the improvement doesn't improve. Okay? It improves up to a certain point, but then it doesn't improve anymore. Okay? And why is that so? And this Amdahl's law is going to describe. It means that it doesn't mean that you have a lot of cores. You can improve your performance, or you can increase your performance gain indefinitely, depending on how many cores you have. Okay? It has certain limit. If you reach that limit, you cannot increase anymore, even though you introduce new core. That is what I'm trying to say. Okay? Okay, let's look at the topic in sequence. Okay, the parallel computing requires that the problem can be decomposed into sub-problem and can be safely solved at the same time. Basically, looking at this, that means it can decompose. If you cannot decompose, you have to look at the condition. Then you cannot do parallel computing. Okay? The programmer structure the code and the data to solve the sub-problem concurrently. Some problem, it looks like it cannot be run concurrently because false dependencies. So you have to adjust it. Okay? Or the example that I was talking about, loop carry dependency. Some loop carry dependency, you can adjust the code. Either you copy the array again, okay? That means you solve them twice in parallel, or you solve them in one iteration. Sorry, in multiple iterations, but in parallel, but only one. You don't break them into groups. But then you have to shift the structure slightly. Okay, so you have to do it. So it says that, right? Now the goal of parallel computing are to solve a problem in less time. Of course, we have to look into that, and to solve a bigger problem and to achieve better solution so that they can compute more. Okay, one example that I've seen recently came up in this. Actually, it's an old story. It's a Singaporean medical school. It's a medical school, but they use parallel computing to find solution for cure of cancer cure. Actually, there is a research effort. It's not really trying to save anything. They just want to find out if they can use parallel computing to advance their research. Okay, so what they want is to find out if they can find a solution to cure certain cancers. Okay, so they have a boy. Actually, the boy unfortunately passed away. He got cancer, and it was a very aggressive kind of cancer. Okay, and in cancer, you got many different kind of medication, different kind of drugs. Let's say drugs A1, drugs A2, drugs A3. Okay? And they try to fight this cancer here. Right? They know that this drug can actually fight cancer, but they are not sure whether it's effective for that particular cancer, because cancer has different kind of cancers. Right? Maybe A1 for certain type of cancer is very effective, but other cancers not effective. A2 was the same thing. One particular cancer is effective, the other cancer type not effective. So they want to find out this. Can we combine them in certain kind of ratio, and then fight this one particular cancer? Okay? So they found out that if they combine in certain ratio, it becomes very effective. Okay, but they cannot do it themselves. They have to use parallel computing to find the solution quickly. Okay? Because the cancer actually grew very fast. And the boy is actually, his life was at risk. Within weeks only, the cancer can grow aggressively. So what they need to find out is to combine them. So what they do is they combine in many different ways, and actually they use AI as well. And then they solve it. Okay? So they try, and then they create like a table. Okay, like a table like this. Okay, different ratio. So the computer AI will actually select it, and then they will put the cell in and see whether it live, grow, or die. Okay, and they have a marker. They put the marker. They can see if let's say the cancer actually growing, the color will change. If the cancer is red, the color will change in different way. So they can actually do it. So the AI can also see it. Okay, can see it. When they put different combinations and they test it, and then they capture. So the result from there can be taken as some kind of solution which can give them the what do you call it? The idea for the next iteration. So here they know that certain combinations can actually kill the cancer. Okay? The next iteration is to use some of the combinations here, okay, add some other things to see whether it can improve further. So after several iterations, they found that there are certain kind of combination can kill. So they use that combination of drugs on the boy. Actually, the cancer cell is from the boy as well. So they put it into this well, a small well, in order to grow them. Okay? So after several iterations, they found some formula, and they used this formula on the boy. Okay? And the boy actually healed for a while, but unfortunately, the cancer came back. Right? Healed meaning that when they check, he's cancer-free. He's cancer-free for several years. Okay? So you can use paracomputing, okay? And you use paracomputing to solve this kind of problem. And the paracomputing is actually used in the AI. Okay? So you can solve problems in less time, of course, because the boy actually the life is risk. Okay, and you can actually scale the problem. Okay, let's say this one is not enough. You want more, you scale even bigger. Okay, depending on your computing power. Okay, of course here you can see the example that I gave to you. It's actually advanced in science, right? Because the scientists actually do not know what kind of combination, and if you want to test this, there's a lot of tests to do. Okay, millions of combinations, but they use AI to actually pick and select, and then try error until they find a solution where it can kill most of the cancer cells. Okay, it's just like imagine that AI is actually doing genetic algorithm on itself. Okay, to find the solution and try to kill as many as possible. In each generation here, it tries to find a solution which is most effective, and then select that for the next iteration. Okay, data sharing actually is good, but if you don't use properly or use it efficiently, you can be disadvantaged in error execution, because we have seen before, it actually depends on one another. Then you cannot do parallel computing efficiently. Okay. Another one is the data itself. You want it to be localized as much as possible. If let's say it's shared across multiple computers over the network, it will not be good. Okay. You want to reduce bandwidth efficiency. Okay. First thing is you want to share, because you want to have multiple copies, which is good. But if you share, you got this problem where you cannot run them in parallel. If let's say they are writing and also reading at the same time. Okay? So you have to balance this out. Some you can share, some you can actually break them. Okay? That means you don't share, and then you can write into the unshared result, and then after that you combine the result. So this one will depend on how you solve the problem. That's why it's double-edged solve problem. Okay, and efficient memory bandwidth usage can achieve synchronization of the task group and coordinating the usage of memory data. So you need some kind of efficiency in data sharing. So you have to use efficient on-chip memory or on-chip data storage that you have, in order to allow this synchronization. Of course, CPU don't have this. If you look at GPU have an efficient way of sharing the data. Okay, if you have read-only sharing, this one most of the time you can have very much higher efficiency, because if you don't write into the data, then you don't have dependency. We have dependency here because of the write. You can see that all the condition here, there's a write. Okay, there's no read. Why? Because if statement 1 read, statement 2 read, there's no conflict there. Okay, so that's why you don't see in Bernstein condition. The Bernstein condition, only if there's one of them is writing, then you have problem. So in this case, if everybody is reading, they share the data and they're reading, and this is the most efficient one. Okay, if you have a problem like this, you are lucky. But most of our problem is not in this kind of condition. Okay, so synchronization, first thing is how do we, let's say we got this kind of problem, how we solve the problem. We need to do some kind of synchronization. Okay, like for example here, I mentioned to you I1 and I3. We know that they are dependent on one another, so you have to synchronize them. How do you synchronize? You have to run this one first. You must make sure that this one is finished, then only the one I3. Okay? Let's say you want to run them parallel also, you can do that. But of course, it's not efficient. Okay, and you use the barrier to wait for one another to catch up. If let's say one is faster, the other one is lagging behind, you will have problem. Okay, so you need to synchronize them by using barrier. Okay, but of course, if let's say you use too much of this barrier, you will have waiting time. There is loss of opportunity of waiting. Okay, because when you wait, basically you are wasting time there, right? So that waiting is actually bad. Okay, the last one, you try to use atomic operation rather than critical section. Okay, because atomic operation normally is faster. Okay, but of course in this case you have to watch out for serialization, because serialization cannot work if you are using atomic operation. Okay, so this is basically showing you how actually you can break down your program. Okay, and some of them you want to do pipelining. Okay, you can go this way, pipelining. And some you can organize by task, and you get task parallelism. Okay, some of them you can organize by task, and you can do divide and conquer. And here you can also assign tasks to actually perform this divide and conquer. Okay, and we got geometric decomposition, where you got big data and then you chop it down into multiple parts, equal parts, and then you assign to different tasks, different threads to execute them. Okay, recursive data is something similar like divide and conquer, but this one is recursive in the form of code. This is recursive in the form of data. Right? So here is by task, by data, by data flow, how the data is used from one place to another. Okay, one thing that we want to look at is the dependency graph. Because the dependency graph can actually show us quickly, visually, how the task depends on one another. Okay? One example is this. Okay, before we get into the example, let's look at this problem first. Not all problem has dependency. In this case, there is no dependency. This problem is the problem that we have solved many times. It's a matrix multiplied by this vector. Okay, so when you multiply, you take this row, multiply by this vector, you get the answer here, right? And then you take the second row, you multiply with this same vector, and you get the answer. Now you can assign task 0, task 1, task 2, task n, right? And this task, although it is using B, the same vector, but it is actually reading, it's not writing into it. So in this case, because it's reading, they all can run in parallel. There's no dependency here. So here no dependency is the best. And you can run that at full speed. Okay? And here if you have, let's say you got 2000 core, you can run this 2000 row of matrix at the same time. Okay, so you got the best performance gain there. But unfortunately, it's not always the case. Okay, you can have a situation like this. Database query processing, for example. Let's say you got database, but this database becomes small. Assume that this can be big. Let's look at the simple example here. If you use SQL before, I believe you must have seen something like this, right? This SQL language, not exactly like this, but something like this. We want to find out a car with model Civic and production year 2001, and the color is green or white. Okay, from this database. Suppose this database is very big, we got a big data, billions of this information. Okay, if you were to execute it using one processor, it will take ages to actually find this for you. Okay, and of course this problem can be efficiently solved by paracomputing system. Okay, this is what we do. First thing is you have to identify what we can actually run in parallel. Okay, so just now I talked about the SQL query, right? We can actually search using one parameter. For example, we want to find a car model. The car model must be Civic. Okay, just now we saw many different car models, right? You got Civic car, you got Corolla, the Altima, this is an old car. Civic, we still have Civic. And then here we assign to one class to find out whether the car, to find out all cars with the model Civic. Okay? So once you find out, you get the ID of the car, because each entry of the car actually has an ID. This ID is unique ID. Okay? Unique ID here. Right? So there's no identifier of the car. Okay? So we can have one pass just looking at the model. Okay? To extract out all the model which is Civic. Okay? Along with it, we also extract the ID. This ID is important so that we can identify the car. Okay, then we can assign another thread just looking at the year. Okay? So this thread is looking at the year and extract. It doesn't care whether it's Civic car or whatever car, it doesn't matter. It just extract the year, which is 2001. So we have another result. Okay. Next, first we want this and in this year. Okay. And also we want it to be white or green. By the moment, we don't care about all that yet. We try to extract the information first. So we have another thread right here, is to find all color which is white. It doesn't matter whether it's Civic or not. As long as it's white, we extract it. And we don't care whether it's in the same year. Okay, as long as it's white, we extract it. Here also the same thing. We also extract whether the car is green. And we don't care about the year, we don't care about the model. Okay? So that is the first phase. Okay, it's done by thread number 0, thread number 1, thread number 2, thread number 3. Okay, this is how we make sure that we can run that in parallel. And in this case here, they are not dependent on one another. For example here, if I have to worry about two things, I need to worry that this white car must be Civic. I need to wait for the result from the Civic so that we can decide to find out whether that white color should be in the list. Right? But then in our case, I already mentioned to you, this thread does not care whether it's a Civic car or not Civic car. We just extract the car if it is white color. Okay? And we also don't care whether it is in this year. Okay? So basically, they just go and grab all the data and then execute that because they are not dependent on one another. They can execute independently. Okay? So that is the first phase. Then the next phase, we can scoop down a little bit. Okay, this is run by another thread. This guy will get the result from this and this two results. Okay? And we say that it must be CV and 2001. So right now we find whether they overlap. So what number is overlap? Let's see this one. Is it overlapping? No. This one overlapping? Yes, overlapping. This one is this one. Okay, this one is overlapping? Yes, overlapping. This one, no, it doesn't overlap. Only these two overlap. That's why eventually you able to expect this. So this depends on these two, yes, but these two is not dependent on one another. Okay? Of course, the second iteration will depend on the previous result. That means these two cannot be run independently. You have to run in sequential. Okay? But across here, you can run in parallel. Okay? Now, how about these two here? Okay, this one is actually finding out CV in 2001. Here, we are looking at the color. Okay, remember it's white or green, right? So here it's very simple, you just combine them together. And these two, they can run together. Okay? Because we don't worry whether this color is CV or 2001. We don't really care about it. We just care about the color. And we can combine them. And we take these two colors, when we combine, if it repeats, then of course you have to remove. Of course, the car cannot be two colors at the same time. So you combine them, definitely this can be larger. But of course, if let's say it repeats, in this case of course no. If let's say it repeats, then you only come out one. That means if it appear here and appear here, you only take one copy, not two copies. Okay, so your result there can be smaller than this. Okay, once you're done this in parallel, now we can go to the next iteration, and this one actually relies on these two results. And now you can check. It should be this and this. Okay? This keyword here, right? So now you can check which one. The first one, no. Second one, no. Third one, no. Fourth one, yes. Fifth one, no. The last one, no. So this is the one. And finally, you get the answer. So you can see that you can run them in parallel. Okay? Here, of course, you can run in parallel. This one is independent. But this one can run in parallel. Okay? But of course, this one is not parallel again. So there's a line must be. So you can see that we can run them in parallel, but at the same time, we also have some kind of dependency. But we're still able to solve the problem, especially if the database is very big. Okay? If the database is very big, then we can actually solve them slightly faster. Okay? We don't get 100% parallelism, but we get some kind of parallelism from here by using this content. Okay, of course, in this example here, I show you we can solve it this way, but we also can solve it in another way as well. So look at this. The same problem, but we solve it slightly differently. Okay? Here we look at the color first. Okay? This or this. Okay, so this or this will be executed independently, just like just now. But the next stage, we click these two results, and we find this. We just test them out. Okay, or find the whole set of this, and we get that. And then from here, this result, we find out whether this car here, white or green, produced in 2001, and then we get the result. Okay? And then from this result, we find out whether it's we find out the CV. Now, what is the difference between these two? Actually, not much different. Some of them can be run in parallel, some of them cannot be run in parallel, so it's actually run in sequential like this. But if we look a little bit closer, we find out that some information is a little bit smaller. Right? Now, for example, here, I'm not sure whether it's smaller or not, but it can be smaller. This is one size, this is another size. Let's look at the bottom there. Is it the same? Almost same. This size doesn't change, but this size is a little different. Just now, it's smaller, this one is bigger. Okay? So, whenever you decompose, you have to look at whether your performance improve not only performance in terms of time, but in terms of space as well. So here actually you use a little bit more space in order to solve the problem. And also, if you look carefully, how many stages that you have? 1, 2, 3, 4. In order to get to the final solution, we got 4 stages. But if you look at the previous one, there's only 3 stages. First, second, and then third. The third one, you already got the solution. So it depends on how you actually solve the problem, like what is stated out there. Okay, you can combine that in a different way in order to get your solution. Some will be better than the others. Okay, so it depends on how you actually decompose the problem and how you execute the execution. Okay, so here is 4 different stages in order to get the result, same result. Okay, here is nothing to do with what we have talked about. This one talked about granularity. Earlier on, we talked about the tasks where we have n tasks, and then each track is going to execute. Okay, that is fine granularity. Okay, and we can have a coarse granularity, especially if you don't have enough core to run in parallel. Suppose we only have 4 cores to run in parallel, and we have this matrix. We have to split them, or we have to decompose the data of the domain into equal size only. So this one will be 3 rows done by task 1. 3 rows, task 2, 3 rows, task 3, and the final task 4. Okay? So task 1 have to do it one by one. Right? So here is sequential, but among the tasks will be in parallel. So that is a possible decomposition. Of course, why we have to do this? Because you don't have enough core, right? So it depends on your resources that you have as well. Okay, looking at the problem before, just now I showed to you they have many different stages, right? So we want to find out first is how high the graph, the dependency graph. Second thing is how wide. Okay, here we want to talk about how wide. Okay, degree of concurrency means how wide. Yeah. Okay, how wide can we get? This is one stage, how wide can we get? So in this stage is 4. In this stage is 2, in this stage is 1. Okay? So that is how wide it is. Here is 4, 1, 1, 1. Okay? Different stages, different width. Okay? So that is the degree of concurrency. How wide it is degree of concurrency. Remember, I mentioned to you how wide it is. I calculate 4, right? That 4 can actually run concurrently, right? So the degree of concurrency for level 1 is 4. Level 2 is 2, level 3 is 1 for the first case. Second case, level 1 is 4, level 2 is 1, level 3 is 1, level 4 is 1. Okay, so that is the degree of concurrency for each level. But also, of course, you want to find out the maximum degree of concurrency. First case, how many? 4. Yeah, 4. Second case? Also 4. Is it correct? So that is the maximum concurrency. Right? How wide is 4? That's the maximum, right? This 2 is 1. So the maximum is 1. Okay, how about this? Maximum? Also 4. Okay, let's look at another metric. How about the average degree of concurrency? The average means you have to take this, add with this, divide by how many stages that you have. So how many there? 3 plus 2 plus 1. Sorry, 4 plus 2 plus 1 is 7. Is it correct? 7 divided by 3? Yeah, so that is the degree of, average degree of concurrency. How about the second example? The average degree of concurrency. 4 plus 1 plus 1 plus 1. So here is 7 also, but divided by 4. Not divided by 3, but divided by 4. Okay? So divided by 4, that means this average degree of concurrency for the second problem is not as good as the first one. Okay? So if you want to compare which one is better, we look at this metric that I was talking about. Okay? Okay, the third one is, sorry, just now talking about the degree of concurrency. I finished that. Okay, the next metric that we can use is critical path length. Okay, so I talk about degree of concurrency, and we can talk about the degree of concurrency for each stage, the maximum degree of concurrency for all, and then the average concurrency. Now we talk about another metric, which is a critical path length. So the critical path length is the task differential graph that we see just now. You have to look at it and see which one is the longest. Okay, which one is the longest? So it determines the shortest time that the program can take to solve the problem. Okay, so let's have a look at this example here. Now suppose each one of them takes 10 minutes of time to execute. Okay, 10 minutes time, 10 minutes time, 10 minutes time. This also says 10 minutes time. So what is the longest or the critical path here? Or when we don't talk about critical path, talk about the longest dependency time. It's 10, 10, 10, 30, right? Which one is the critical path? Which one is the critical path? Actually, the critical path there are a lot. Here is one critical path. Here also the critical path is the same, right? Because here is 30, here is also 30, right? How about here? Also 30. So here is also critical path. All of them are the same critical path, right? Okay, how about the second one, this example? So suppose this is 10, 10, 10, 10, 10, 10, 10. Okay? Okay, the first question is, which is the, what is the largest, or I should say the shortest time in order to execute this problem? Huh? Is 40, right? 10, 10, 10, 10, is that? Okay, is this critical path? No. Is this one critical path? No. How about this one? Yeah, this is possible critical path. This is critical path. Right? So that is the critical path, and also the time unit that you need to execute the problem. So when we draw that graph, actually we draw that graph is to find out the metric and also which one that we can improve. How do we improve it? Okay, can we improve it? Can we shorten the critical path? Because the critical path is actually the shortest path, the shortest time to execute the cloud computing problem. Okay? Okay, this is one example. What are the critical path length for tasks, two task dependency graph? If each task takes 10 time units, what is the shortest parallel execution time for each decomposition? So we got two decomposition here. Okay, the same as what I mentioned to you just now. Actually, it's the same problem, right? Okay, so we already answered this question. Okay, what is the maximum degree of concurrency for this? I think we already answered. It's 4, right? This one is also 4. The average, this one is 2 or something. This one is a bit bigger, 3 or something. If the question comes up, it's quite simple. You should be able to answer. Okay, there's a limit of parallel performance. Okay, it would appear that the parallel time can be made arbitrarily small by making or decomposition finite and finite. So if we make it finite, we can actually use a lot of calls to solve them. For example, the matrix, we got 2 squares, right? So each one of them you can run concurrently. This one you're lucky. Okay, because matrix computation mostly are independent of one another. So it's lucky. But if you have problem like the databases now, it doesn't mean that if you make it finite, you can always get a computation advantage by trying to parallelize all the execution. You find out that we have problems because they are dependent on one another. Okay, another thing is you have to consider the communication overhead among them. Okay, they need to communicate with one another in order to get it done. There's a question from some group asking me why when I run in GPU using one thread is longer than running in CPU. Okay, actually there are two reasons. The first reason is GPU do not have optimization, execution optimization in their processors. Okay, they have a lot of cores, but the cores doesn't run efficiently. Okay, so they rely on the number of cores. In a single processor, it has a lot of optimization, hardware optimization. So if you talk about single thread, surely it will win. CPU will win. Okay, GPU will not win. Second reason why it is slower is because of the overhead. You have to copy it into the memory, do some initialization, and then run it. So it's slow, right? That's why this overhead is important. If your problem is very small, don't use GPU. If your problem is big, then only use GPU. Okay? Because if you use GPU, you have this overhead because of granularity. Actually, it's already waving on something. Okay, I will go out, but before that, yeah, okay, you can hit now. I already finished.